Go ahead.
Am I audible?
Yeah. Yes, go ahead.
Okay. Thank you. My name is Anjana Ravi. I'm a research scholar at NITK, National Institute of Karnataka. And I'm going to present today activated carbon fabricated from cow dung supported polymolybdate electrode material for a electrochemical applications. These are my contents: introduction, followed by experiment, result and discussion, conclusion, and references. So introduction, we know nowadays one day also we can't even think about the energy. So we will get the energy from the different sources, for example, nuclear energy, coal energy, wind energy, etc. But why we need a storage energy? If you want to perform it for use a phone or laptop or watch or torch or something, we want a storage energy. That's why our group is very much interested in batteries and supercapacitor. So what are the main difference between the batteries and supercapacitor? In case of battery, it is a chemical storage and high energy density and low power density and low cycle life due to degradation. So once if it charges over, in the case of battery, we have to throw that battery. It is going to a environmental waste in our earth. But in the case of supercapacitor, it is a surface storage and low energy density, high power density, and it is having a high cycle life. That's why it is not going to be a environmental waste. That's why our team is mostly concentrating in the supercapacitor. So for an example, how we can separate the supercapacitor and battery. If we are going for a 200 meet race, that we can consider as a supercapacitor, because there we need more power, then only we can finish it faster. But in the case of, so it is an example for supercapacitor. But if you are going for a 20-kilometer marathon or what, we need more energy to finish that marathon. So it is like a battery. It is having a long life, like it will run for a long time once it is charging. And what are the advantages of supercapacitor over batteries? It is having high power density. It is simple charging methods, and it is having appreciable working temperature, almost minus 40 degrees Celsius to 70 degrees Celsius. It is having a very high rate of charge and discharge, and it is good reversibility and eco-friendly, and whatever the material we are using, those also very less toxic, and it is having high cyclic efficiency over almost nearly 95%. And the working principle, how it will work. So we are going to use here a 2-electrode system. That's why I am explaining for a 2-electrode system. Here you can see one electrode material in the figure. The electrode material, we will got 2 electrode material will be there. It is separated by a separator. That separator is internally connected by, like it is having, we are immersing the electrolytes. That's why it is internally connected by the electrolytes. So electrolytes are this is a medium containing the positive and negative ions, and also both the electrons are connected with a metallic film, and this metallic current collector is connected by an external circuit, so we can measure the current. And it is normally, according to a charge storage mechanism, the supercapacitor can be classified into 3. That is, I'm showing here one supercapacitor tree, and one in that supercapacitors we can divide it into 2. Mainly it is double layer capacitor and pseudo capacitor. So double layer capacitor, mainly we can use the material like activated carbon aerosols, carbon nanotubes, graphene oxides, etc. Graphene and reduced graphene, etc. But in the case of pseudo capacitor, we can use conducting polymer, metal oxides, metal sulfates, and also polyoxometallized, these kind of things. So here in our research, we are using a activated carbon prepared from the cow dung ash. So if you are selecting one material from the double layer capacitor and one from the pseudo layer capacitor, that material is going to be becoming a hybrid capacitor. It will show both the properties. So it will show a very good capacitance in the case of supercapacitor. And next, this is once again I am showing the elemental classification. In the case of double layer capacitor, that is EDLC, we can take the activated carbon, these kind of things, and the pseudo capacitor we can use the polyoxometal, conductivity, etc. And What is polyoxometalate? Polyoxometallates are a rich class of inorganic metal oxide cluster compound with a transition metal in their highest oxidation state. And the general formula of the polyoxometalate is XXMM and OYN minus. In this, X is the hetero atom. We can call it is an hetero and it can be from the main group, example phosphorus, sulfur, germanium, arsenic, etc. And the M is the added atom and it is from the D block element, and it should have an oxidation number, very high oxidation number. So he is Dr. James Keggin. He was for the first Keggin structure, and we are using here whatever the I am using the polyoxometalate. It is coming the Keggin family, so I am going to show the Keggin structure here. Here you can see the orange color middle atom, that is the hetero atom, and whatever the pink you can see, these all are the addend atoms, and whatever the red ones are there, that is the oxygen atom. So this is the simple structure of the polyoxometalate. In one molecule, it contains many atoms. And what are the experimental protocols I am telling? The cow dung ash I am preparing from the normal burning techniques, and we are collected the cow dung from the villages, and H4PVMO11 or 432H2O we are prepared as a we are using as a form. It is synthesized from the literature, already reported literature. And ACVMO11, that is the composite what we are prepared. That was prepared for the normal simple stirring method. So here you can see the schematic diagram. Here just we are taking the cow dung ash, or we can sell AC in methanol. It is a solvent, just a solvent, and we are adding the particular amount of foam to the that solution and stirring almost 24 hours in room temperature. After that, we are just evaporating the solvent and drying the powder. So whatever in the surface of the activated this cow dung ash, all the foams are settled. So that we are using as an electrode, and we are coating in a carbon cloth. That is our method of preparation of electrode. Now the resultant discussion, we confirm the product, whatever the products are formed, that we confirm by FTIR. Here you can see the red one is our polyoxometalate FTIR, and the lower one, white one is the just the cow dung ash. The first one is the composite, whatever the we prepared. So all the peaks are matching with that. So the form, whatever the form we supported, that is present in the composite. And we confirmed by using FESM and EDS also. In the case of FESM, you can see in cow dung ash only you can see the surface morphology. It is having so much pore sizes. In the case of only the polyoxometalate, it is like a small blocks. When we are preparing the composite, it is the structure of that composite is totally different, and the EDX also matching with that. Whatever the composite elements are present in that, it will be present in the composite also. And we did the TGS study also, and bet also we have done here. This is also confirmed that whatever composite we prepared, that is correct. And we are done the cyclic voltammetry.
Anjana, you have only 2 minutes left.
Okay, sir. Cyclic voltammetry also by using 0.1 molar H2SO4. This is the CV graph for the composite. First one is the composite, second one is the ash. So this is the graph between the scan rate and specific capacitance. Here it is clear that the composite is giving the highest amount of capacitance, that is almost nearly 20. And we have done GCD also, galvanostatic. Here also the comparative study of our composite as well as the ash. So here also it is clear that one more graph I can show here, the specific capacitance current density when we are doing. Here it is showing in 0.4 current density, our composite is showing almost nearly 140 specific capacitance. This is one more graph for energy density versus the power density. Here also it is showing very good power energy density, that is almost 80, and the power density is 800. And application, we know nowadays the supercapacitor is using in most of the vehicle. Also, many countries are already started. And the conclusion, our material, whatever we prepared, that material is a novel electrode material. And when when we are introducing polyoxometalate to the AC, it is going to be a very good electrochemical electrode material. And one more thing, the cow dung is a waste material. From there, we are using we are preparing a new material. That material is we are expecting it will be a very good electrode material for the future. These are my references, and thank you.
Thank you, Anjana. Now the
Thank you, sir.
presentation is open for one or two questions from the audience.
Anjana, this is Ramesh. I have one question.
Yeah, yes, sir.
Yeah, so many people only focus on the cow dung, but why you are not focused other animal dung?
Sir, we just in polyoxometalate, normally in cow dung also there is no papers are reported, sir. So we thought we will first try with cow dung, later we will go for other some ashes or something. Here only we got very good result in this case.
Okay, because of based on cow dung is a more methane.
That is also we can tell. Yeah,
Yes,
we
yes.
will
Main
get
reason that
easily
is
know that.
it's improving the capacity,
Yeah.
the quality. That is very main reason.
Yeah.
This is also
Yes,
okay,
sir.
thank you.
And normally we will get very fast cow dung only. In our area, cow is more. That's
Yes,
why
yes.
we will get easily
Yeah,
that
that is
one.
agriculture
Yeah,
based.
that is also one reason, sir.
Okay, okay, okay.
Hello,
But Anjana, I have
hello,
one
sir.
question. Actually, it should have been nice,
Hello, sir.
if you compared with, some activated carbon which is being at present used here in like capacitors, okay? And then compare why
Yeah.
the ash produced from cow dung is better than the other one. You need to compare and then show, and then you
Yeah.
explain. Simple surface area will not
Okay.
work here. You need to show the reason for that.
Okay, sir.
See, you need to take an active charcoal,
Okay,
just
sir.
carbon, which is being used now in all the capacitors. Compare this one.
Okay.
What way this
Okay.
is better actually?
Okay, sir.
Okay.
Oh,
Okay.
okay, sir.
Yeah.
Okay.
If
Okay.
there are no more
Thank you, sir.
questions, no. Thank you, Anjana, for your presentation. Thank you. All the best.